So good morning also from my side. Glad that you are all back. I'm very happy to be here. My name is Sebastian Schöps. I have a chair in Darmstadt, which is essentially dealing with simulation technology. So originally we dealt mainly with, or we still deal with electromagnetic problems. But you will see that it is not, I mean, the examples will be from that domain, but I think the methods and ideas super easily can be transferred. Originally, we dealt with PDEs, which is in this case Maxwell equations. I will show you a few slides on that. I try to bother you not too much. um, but then we also already at that point a lot with software vendors in that field. So there are like 3-4 big companies nowadays. I mean, they were more in the beginning, but now they I mean, Siemens bought everything essentially. So, and Dassault and Ansys also. Anyway, we collaborated with these companies also a lot regarding D-based solvers. And then I think I was skeptical whether I should go down the route and do research on machine learning, right? But at some point it was like, it's this push and pull something. And sometimes in this case it was pull because industry was also very much interested. And we did some things that and we looked into ideas how to integrate, let's say, machine learning techniques into this workflow. And I'd like to talk about this with you today and tomorrow. So that's what I want to do with you. So today, I yes, I can close the door. First question from the audience, whether I can close the door, and the answer is yes. That's a good start. Okay, so today or this morning, I'd like to talk with you about simulation-based design workflows. And I really hope that that's interesting for you because you can see how the dots are connected. And again, we can also try together to make this more abstract and link this maybe to fluid dynamics or fluid mechanics, what is maybe your main field of interest. Then I will do an introduction to stochastics. Let's see, I guess this might take a bit longer. This will hopefully be a bit shorter. Really basic stuff. But since later I would like to talk about uncertainty quantification and some advanced case studies, I really think that we should talk about stochastics because my experience, I mean, it may be maybe all experts and maybe I'm the weak link in the room, I don't know. But my experiences with students, at least in Darmstadt, that stochastics may be back in school, right? So that's why I want to repeat a few things. So let's be strong in that session, okay? And let's get quickly through it. But that's my plan. A bit about stochastics and statistics. Then I think we can come to and discuss more interesting things. So uncertainty quantification techniques, and then I will show you some. And that's so here. This is hopefully for you. Let's say the interesting part, and this is the thing we have to do, right? So this is hopefully also a bit interesting. And this is hopefully really interesting because you see how things can be put into place. And I think many definitions I make here also become later on clear if you do the case studies. Then I'd like to talk about robust optimization. I think this will be maybe a bit shorter, but then I will do a more longer case study. And I think it's always like 2 or 3 case studies I'd like to show you in there. That's the program I've envisioned. Similarly, as Giuliano in the talk before, I try to focus on concepts and hide a bit the technicalities. So because indeed the literature is vast, right? And it's like, I don't know if you are on ResearchGate or any other platform. It's like every morning you check, it's like, oh my God, like 5 new papers that sound super interesting. And it's like you cut off one head and like 2 grow up now, right? So it's difficult to keep track. So I really try to use some of the basics because then you can find your way. Also, I have to admit, I mean, especially if you collaborate with industry, it's not that they are interested like in the most fancy version of something, right? They want to, I mean, they have to maintain code, right? So sometimes they rather prefer the easy solution, which is not the highest, because not the highest efficiency, but it's maybe the robust one, or is the one that the employees can actually maintain. All right. So okay. So for this morning session, so I will start with motivation, why electrical machines matter. Then I talk a bit about simulations in industry workflows and some first ideas on uncertainty and optimization. And if I manage, and if I might done and so on. Maybe we can also do some original, some first discussion on that topic here. Maybe we can exchange some ideas. So I had some maybe bold statements that we can discuss. Okay, so I mean, originally I was also not somebody simulating electric machines, but suddenly, you know, everyone wants to do it. That's because of the energy transition, right? So that's quite obvious, I guess. And which is surprisingly fact. So I don't know if you also were aware before. So 50% of electric energy is actually converted by electric machines to mechanical energy. So if you save a bit, that makes sense. So that scales quite attractively. And then there is a back and forth whether we will have fossil fuel powered cars after 2035 or not. So at some point, it seems we would not have. Maybe now we will have. Let's see what at least in Europe. Okay, I'm talking about Europe. Let's see what the European Union will decide. Maybe already not really ready to the course, but just to make the obvious fact, I think I'm one of the few persons who should have an opinion on that. So I think there is no way we will see other cars for private people than electric ones with battery in the next 20 years, right? So just to be very clear on that, I mean, I'm all for, let's say, you know, all options. The best solution should evolve, but that's right now the best solution, full stop. Okay, so don't let blind you if they tell you otherwise. Anyway, so electric machines, I'm biased, obviously, so let me also state the obvious. But people tend to believe me, especially China tends to believe me. They hear very clearly what I say. And if you look at the statistics, especially in China, the electric vehicles are really taking off. So this is a big market. And that's also the thing, right? People in Europe tend to believe that we are doing so much for the climate regarding traffic, and that's definitely leading the way. Okay, so that's like the marketing part, why electrical machines matter. Let me tell you what we need to do also on a very abstract level. That's why optimization and certainly quantification comes in later. So the US government issued a document a few years ago, and you see here the so-called electric motor targets. And they believe such that electric vehicles shall be affordable for everyone, right? Right now, they tend to be quite expensive. So what do we need to do to make them affordable to everyone? And they made a study, and they say we have to reduce cost by 30%. It's machines now, not the batteries. And we should decrease the volume by 90%, which sounds like crazy, isn't it? And I mean, since many of you are engineers, so it's not just that you make things smaller. I mean, you have less volume to reduce the heat. I mean, that's the actual problem. So I would say one of the biggest problems now in designing electrical machines is not so much the magnetics. So that's well covered since 200 years. It's like how to get rid of the heat. That's the interesting part. So how to get the cooling done and these kind of things, which immediately, I don't know if you have these kind of people in your head who tell you, multiphysics, right? That's the person now screaming in your head, maybe, yes. So you really have to do multiphysics simulation to reach such goals, which is actually, and I will come to that later, is right now not the case in industry. So right now they do typically purely instrumental simulations, and then they do afterward maybe some mechanic studies and so on, maybe also uncertainties, but it's really like a several step process. So the heat optimization is not really closely included in these kind of optimizations. Okay, so electric machines, here's an example how one machine could look like. It's a so-called permanent synchronous machine. It's from an electrical bike, actually. It's from the Robert Bosch GmbH. That's one of the companies we are doing consulting with. And for this talk, I mean, that's also power electronics. We don't care for now. If you would do proper simulation in industry, you would have to do like system simulations and also take care of this, of course. But we don't do this today. We're talking about rather PDE-based model, at least at the very beginning. The interesting part is the rotor, and that's the stator. In the stator, you see you have windings, and then there's a rotor, and the design consists of permanent magnets. So blue and green. You find again blue and green. Blue is the stator, green is the rotor. And I said before, there are great conductor machine. Nowadays, the most popular design is this one. You have permanent magnets in the rotor. Because then you do not need to have power, you don't have to feed power into the rotor. It's convenient. And you have coils in the stator. These coils are powered. They will create a magnetic field. I will tell you in a minute how. And then this will, if you optimize your machine carefully enough and did everything right, it shall actually turn. Be aware, and that's maybe also that's a challenge. I mean, this is probably school knowledge. And the interesting thing is, This is a machine with two faces, so a blue face. I should use a pointer for the online crowd. Faces, so a blue one and a colored face. And you see that the blue face coils are always of alternating connection. So this is plus minus, minus plus, plus minus, minus plus, and the same for the purple face, plus minus, minus plus. In practice, you would just turn the winding the other way around. And this is like crucial. So this kind of scheme is crucial. And now let's have a look why this is crucial. So let's start. I mean, we have two faces. I mentioned that. And in reality, you will have even typically machines of 3 or more faces. But for explanation, 2 faces are totally sufficient. So let's say you can completely perceive, let's say, quasi-static regime. So I'm not talking about time. I'm talking about angle. So the current is moving between 0 and 360 degrees. And let's say at the beginning, the blue current in the blue coil has 1 ampere or whatsoever. I don't care about the units here, so it's 1, okay, or whatever unit you prefer. And then this turns this coil, this creates a magnetic field. There's a north pole over here, and the purple colored curve is just off, right? It's 0 amperes. Then we move along in time. The angle of this changes, and then at some point we reach 90 degrees. And what has happened? Then the purple curve has 1 ampere or whatsoever. This gives me a new north pole over here, and the blue one is switched off. So you have seen that the north pole moved from here to here, and the rotor has turned accordingly. And this can be done, of course, now subsequently. Now, again, the purple curve is switched off, and the blue one has a negative current. But since we have swapped the connections, this gives again a north pole over here, and again, and again, and again. And that's how permanent magnet synchronous machines turn. And these are the machines that are currently used in mainly electric vehicles. There are some other designs as well. I will not give you a broad overview. This is not a machine lecture, I'm fully aware, but this is like the setup I want to discuss with you. And I will connect back also to the lecture of Steffi in the beginning. So what are the degrees of freedom you have here, right? So you can choose some discrete options. So you can choose how many magnets I like to put inside motor. You can choose how many coils you want to have. You can choose how many phases you have. And then there are a lot of other options, right? The shape can be modified. You can put holes inside, and this is not then different ways to optimize such a design. Okay. The production of these machines, theoretically, if you talk to people from industry, they can create machines theoretically with arbitrary precision. But that's, of course, an economic decision, right? You don't want to produce machines at the very, very high precision, because this comes with increasingly, infinite cost, essentially, right? Infinite precision, infinite. So there are several sources of uncertainties that they have to deal with. So I have like 3 ones that we investigated. For example, these permanent magnets are bought on the global market. You buy them in batches, and according to Collins Industry, these batches have high fluctuations. So all these permanent magnets, right, they have like an angle of periodization, which is, if you bought a magnet, you probably didn't care because your fridge doesn't matter how much if the angle is like perfectly aligned or not. But for an electric machine, this makes a difference. So, and all these magnets then may have different angles, and then there's a question: how do you deal with that? Do you buy them for more money? Because what could be done, right? You can first sort them in some way, right? You can measure them. You can check each individual magnet. You can check, okay, it's like this, it's like that. And then you can even theoretically distribute those magnets that you have measured individually there, right, to make like an optimal pattern. But it's like very, very costly. It's not done. So, these are options. So that what you need to deal with is with magnetizations which are not such. Then there is in this particular design that we looked at that time, the stator created pieces, so several pieces which are welded. The reason is mainly that this allows the winding of the coils to be much easier. So the pieces are welded. That gives you these problems, at least 2 problems, even more. But one is that the stator might be slightly misaligned. And secondly, you have the welding interfaces which change the material properties. These are like 3 examples that we investigated. Let me also maybe tell you that in mathematics, the machine simulations is super addictive. I mean, if you do fluid simulations, I I hear from my colleagues that it is sometimes a challenge to really have like a very high predictive value. But here you easily get, if you just value the data sheets, you get percentages like 1% of accuracy with simulation. So it's really, really good. Without, peaking parameters, you get high accuracy. And this, I mean, if I recall our studies correctly, this accounts for like 5% of deviation, for example. I mean, I give you just rough numbers, okay? But just get a feeling. So these are big enough that you would really realize that in your results. It makes sense to take care of them. So I mentioned that before, right? This is just another picture how this is a concept that's called yield. So the yield, a little bit is defined later in more detail. There's the idea that you define some kind of properties of your machine or whatever object you have, in which it will function, like the necessary condition for the device to function. Very often these parameters are given along some range. So let's suppose that the air conditioning in a German train, right, and should work from winter to summer, right? That seems to be the task, and should be always below some threshold and should be working. Seems to be an interesting optimization problem. So the kind of range parameters, I mean, for a machine, it could be the working point, right? Are you going uphill or downhill? You still want that the energy is below something. And quantity of interest could be then, as I said before, could be the energy. And now the idea is you want to optimize machines, so you cannot change that bound. But what you can do is you can make sure that another design maybe has this curve, or if you do a bad design, it may have this curve, right? And this is like, things you want to take care already in the optimization, make your device work also under some difficult circumstances, and then to reduce the so-called failure. All right. Questions so far? I mean, workflow stuff, but I think that's. I hope it's interesting because you will later see. I mean, you already probably can guess, right? Optimization is costly. Multi-objective optimization, it's even more costly. And then you want to do also uncertainty quantification in one loop. This is very, very expensive. And that's things I want to address here. That's why I put that scene. So, okay, so industrial workflow. Again, I believe this is not only true for electric machines, it's true for many, many designs nowadays done in industry. So people start on stage one with template-based designs, and which essentially the simulation that they do is probably spreadsheets, right? So it's not EDE, it's eSolver, so it's really very simply constructed. I know, at least in my field, that there's even I mean, people essentially sell you an Excel spreadsheet, right? That's the software that they sell you to do these kind of computations. So that's what is done at the beginning. You choose how many coils you have, these kind of parameters. So that's very, very template based. So I will stress that a lot. And then I think nowadays we are slowly moving from that to shape and topology optimization, and the whole things that also Steffi mentioned and will be also topic of this course regarding all this freeform deformation, these kind of spline technology will be crucial to do that better respectively. Anyway, so I think it's interesting about this diagram from a rather recent book that they say, well, then comes the stage where they only do electromagnetics. Then there comes a stage when they take this design and then they try to make the cooling somehow work. And then the last stage, they actually check if it's manufacturable. It's manufacturable. Yeah, that's the word. And they do, for example, some structural mechanics simulations. But it's really coupled, right? And if you would have done all those things much earlier in that design flow, you probably would have gotten designs. That's how it's currently done. Also because, as you also may be aware, so in industry, this is typically done by, well, sometimes by in-house software, but mostly by commercial software. And it's even like that in many companies, although the software vendors try to change that, of course, that people use different software on the different stages from different vendors. So, I mean, the structural mechanics, people really love their ANSYS. Electric machine designer uses AMAC, that's a bigger company from Japan. And this gives a lot of nightmares regarding, mesh interpolation and all these things. And it's not typically not based on scientific arguments. It's just based on, we did it always like that. So that's our software. We like it, we know it. And so this workflow is somehow also, you know, to of the good software that we have, right? So it's so good, it's good enough that people can work with it, and the pain is not big enough yet. I think that there's a big change, right? Okay, so I mean, I think this is a very obvious lie, but I just wanted to define the three words. So what is commonly done, and I will mainly talk actually about parameter optimization because this is what is mainly done in industry. So you change a few widths or heights. Then there's shape optimization, where you really allow freeform optimization using splines. That's a field where we have been also working quite actively on, not yet combined with machine learning techniques, I have to admit, or some very strange specification cases. And then there's where you really can put additional holes or different materials at different speeds. These things are, I mean, you can combine those, but they are rather third worlds, right? And that's like, I would say, state of the art. This is a picture from colleagues from industry. So that explains their workflow, I think, in a very nice fashion. So how does it work? The customer comes with requirements on the product. And it's really, I mean, I like to stress that. In former times, a company may have had one product and an external company may have bought it or not. But nowadays, it's really that if a customer comes, I mean, if the customer is big enough, so let's say that the motor is created here by Bosch GmbH, and this customer may be Porsche, right? Then it's big enough that Bosch says, okay, let's find you a machine that you actually like. Then they come with requirements. These requirements are then put into multi-objective, multi-domain optimization, mainly template-based, where they do all the multi-physics. So you see there's magnetics, there are loss computation, there's thermal mechanics. I don't say they are strongly linked, right? I just say they are done, maybe in a sequential manner, but they're done, and not surprisingly, also cost optimization is done. Anti-acoustics maybe also interesting. Yeah, so all this is done, and they really evaluate a lot of design. So this kind of workflow tends to take, let's say, a few weeks, maybe 2 weeks, or 2 weeks, or 1 or 3, depends on the company, depends on the workflow. But this is the time they do kind of these kind of optimizations. What they can do is like they run 100,000 designs per week. So to my knowledge, the machine community, this is done without any model or reduction, right? It's typically 2D designs. Maybe that's also interesting. And for some machines, you need actually 3D simulations, but for some 2D are sufficient. So they run really a lot, full-featured time domain simulations. Then to get some Pareto fronts. If you're not familiar with fronts, I will have one slide explaining it. But, well, you select the best ones, and what best means is a bit of a difficult situation if you have conflicting goals, and it's the whole point of Pareto fronts. And then they deliver machine designs. So I personally, also I think most of the optimizations I will show you are dealing with. I mean, there we use a lot of machine learning, by the way. But we have used gradient-based optimizations because in former times I thought these kind of swarm genetic algorithms are like not very interesting. They are so simple. They don't use so much knowledge. But it turns out, and I have to admit that, you know, getting older, you realize that maybe all simple ideas have some value. So they really perform very well. And the thing that I was not aware, that you just really understood after having collaborated with history, is that really a lot of points. I mean, just assume you have 30 conflicting goals, okay? So it's really a high dimensional problem. If you draw random samples, surprisingly many random samples will lie on some of the Pareto fronts. So, and that's the thing that I was somehow not aware. So I thought like, yeah, you do this stupid swarm kind of stuff, you throw points, and well, you look what happens. But throwing points is not so stupid if you have so many conflicting goals. And that's the thing that we in academia, or let's say that I do in academia, okay, I will not blame you, I will blame me. And if you do multi-objective optimizations, we do like three yeah, or maybe 4. That's the workflows that we have in our group, but industry has 30. So the probability to land on a Pareto front, this kind of problem is much higher. So in these cases, it's not, you don't waste so many points as you could have imagined, or again, I don't blame you, I blame me, I would have imagined. So, but let me say these nice words about swarm algorithms, which I have not assumed that I would ever do this in the class. Anyway, so, and then somebody picks a machine design, right, from some Pareto front because it's the nicest, the cheapest, whatever, and then the company will be manufactured. Okay, so this can be simulated properly, and now I slowly connect maybe also to Giuliani's talk, and we see some equations and how things work together. So in electromagnetism, you have 4 fundamental laws. I promised I will not torture you too much about it. So I will just very quickly go through them. So the first law says essentially if you move a magnetic field, so for example, a permanent magnet, then you will induce a rotational electric field. And there's even, well, in the opposite direction, that's why there's a minus sign. Then there's somehow the inverse law, if you like. So if you put the current through a wire, then it will create, again, a magnetic field. And if you form from the wire a coil, these kind of fields nicely connect to each other, and you get this kind of magnetic field, which looks essentially like a permanent magnet field you would also get, right? Then there is Gauss's law, which is the divergence freeness, which also Giuliano discussed in different physics, but that you recognize these things again in different kind of settings, right? So we have somehow, well, the divergence law, a special case in the case of Gauss's law for electric cases, that you may have sources and sinks. So it does not have to be divergence free, but the magnetic field B has to be divergence free. So here we have sinks and sources. Here I will use that law, I think, in the next slide or the one after. So let's remember that maybe. It's the only thing for right now. We observe that these equations are second order in time, yes. If you plug all these equations into each other, so they can have hyperbolic effects. Luckily, because hyperbolic is difficult, as we heard this morning, for electric machines, that's not the case. So you can neglect one derivative because things are not moving with the speed of light. They are significantly slower, and that makes our life much easier. And model order reduction techniques, for example, much better. But this slide essentially, so there are 3 effects included. There is the magnetic world, like inductive things, there's the electric world, capacitive effects, and there's the ohmic, the loss part. Magnetic machines, you either just look to magnetic stuff or magnetics and the losses, because of course you need the losses to compute the energy efficiency. And that gives us a subset of these equations, and that's also very similar to Navier-Stokes, right? And in fluid mechanics, you rarely have to solve the full set of equations, to my understanding. There are, in many cases, you have special cases where you can luckily make your life easier, right? Okay, I mentioned before that there's one law that says that the divergence of B is supposed to be 0. So what I can do now is to define a new variable that I call A. And they say, well, the curl of A shall be B, and then if I take the divergence of B, the divergence of a curl vanishes, and this law I showed you before is just automatically fulfilled. This is the main idea that is used in all low-frequency electromagnetics simulations. The only drawback is that you're aware that there's something like Reynolds theorem, which says, well, you have a general vector field is defined or has divergences and curl, and here I only defined the curl of A, and indeed this is an issue. So this kind of formulation based on A have the issue that they are not unique. So they are solvable, but not uniquely solvable, because you can add always a gradient field to that A, and you will still get the same B, right? So that's what's written here. So I add some psi, I take the gradient, and then the curl of a gradient will just vanish. So whatever I do, whatever I add here, I still get the same B. So I can have an A prime that is different from A, but still get the same result. Okay, I will not go down this rabbit hole. That's an issue, but this can be overcome, and it's well understood. Okay, so and that's maybe now we are coming a bit back to the world that you're maybe familiar with. So this is the equation after plugging all the equations in the static case into each other. So we have one curl operator here. There's another curl over there. There's a material property in between. That's my unknown vector valued field, and this is some excitation or load vector, right? So this is not so different from the Laplace equation, yes? It's a bit different because we have the curl instead of divergence and gradient, but for us right now here, it's totally sufficient that we think about this as a kind of vector valued. Then you do the same steps you always do. I do the weighted residuals approach. So I multiply by test functions. Since I'm dealing with the curl, I have to choose specific test functions, not the conventional test functions, or not the conventional splines. You may be aware of something special, but also this is not of my interest today. You need to take care of boundary conditions, and then after some calculus, you get the weak form, right? So that was like the multiplication by test functions. Then you use some vector identities, and you get rid of some derivatives, and in the end, you see without theorem, the weak form, right, that you have. So here again, that it may look somewhat familiar to you. So this maybe, if you know Laplace's equation, this may be then the gradient. This may be a gradient of test functions, gradient of your solution, material parameter, and then we have boundary conditions and the load vector. Okay. So defining the boundary conditions, let's make our life simple. So we assume that they go to 0. So we have 0 Dirichlet conditions, for example, so we can essentially get now for electric machines to move, and that's one of the connections I want to make to the supermisors we heard this morning, is they pop up also here. So if you do a moving formulation, because in the machine the rotor will turn in the stator, you cannot solve the problem on one fixed domain, but you have to deal with, let's say, domains. So here again, weak form. And I said before, like the conventional boundary condition on the outside world, I will assume this one to be 0 and to vanish. But if I tear my domain into 2 pieces, right, I have to define an interface condition. And this interface condition has look like the same as a boundary condition would, right? So, and what you do, you introduce a Lagrange multiplier, which essentially defines, in some sense, the flux connecting those 2 domains, right? This is the internal boundary now. But imagine that this is all curved. Yeah, we are talking about electric machines, but what do you mean also see this as a linear problem? And then we have the problem on 2 domains connected with the flux that goes in and out. So we have to choose the sign, in one case positive and the other case negative. And we are still lacking one condition, and that's the famous mortar method that you obtain here. So what you do, you ask that the fields on both sides, let's say in a weak sense, are the same, and that's exactly what happens here, right? So I have introduced here the Lagrange multiplier. Now I use the same space I've used to construct that Lagrange multiplier to test the equation here, and then this is my weak form of it. And you may see that this is a saddle point problem. So if you want to apply, first of all, if you want to solve it, you have to make sure that the spaces match, and that's also similar to the Taylor-Hood kind of story that we heard this morning. You have to choose the elements with, let's say, according degrees at this table. But that's, again, not necessarily, I mean, do that in a discrete case. It's even not necessarily order reduction. And it's a thing I want to mention because I think it's a very nice connection. So we also did model order reduction for electric machines using some of the technology we heard this morning. What we've done is to parameterize the machine in the rotation angle, right? I mean, that's the parameter you cannot get rid of. That's an ugly one theoretically, but because it's a very specific one, right? It's somehow only the coupling condition. So it's not in the matrices. If you remember in Juliano's talk, these kind of depend on what in those matrices. This kind of formulation also makes sense, right? Essentially, you may perceive this as 2 separate domains, and you do not actually move the domains, you just move the connection between the domains, right? And that virtually makes the rotor turn. And this is why we do not have parameter dependence in there. The only parameter dependence we would have in the classical finite element matrices would be the shape parameters. But there we also did an affine decomposition as proposed this morning. What you see here is a specific form of the saddle point problem. I mean, you see there's a stiffness matrix, let's call it like that, and that's another stiffness matrix. Again, the touch issue. Anyway, so, and I will use the pointer. So those matrices originally would have been here on the diagonal, yes? And these would be then the coupling terms there and over there. But what I did here is I formally inverted those stiffness matrices. This led to a very interesting method. So either we used model order reduction for this, which is in the nonlinear case almost necessary. But if the problem has no additional nonlinearity in terms of material properties, what works quite well to formally invert that matrix. So you don't really include an inverse, but what you do, if you have, okay, let's start here. This is the Lagrange multiplier, and these are the unknowns. So these are finite element many. So in 3D, these are 3D degrees of freedom. And then this would be an interface, so 2D many. In 2D, those are 2D many, right, in the plane, and the Lagrange multiplier is only on the interface. If you choose actual method. So you discretize the Lagrange multiplier essentially by sinusoidal functions. This is a very powerful, very quickly converging method. So you really need only very, very few Lagrange multipliers. And that allows you, this means though, this by lambda is only, let's say, n, whatever. That means you only have to solve 10 linear systems to compute this. This is actually computation that is feasible. And then you can essentially go down. You don't even need model reduction. You can do a Schur complex situation, right? Because now once I have the identities over there, I can eliminate those two guys. I get a fill in over there, so the conventional Schur complement, and I only have to solve systems 10 degrees of freedom. So if you have nonlinearities, this is infeasible because then those matrices also depend on the state, and then we really have to do techniques as discussed modeling. But I thought that that's a very interesting connection we should make, and this would be a very nice technique to, they do hundreds, thousands simulations per week of systems like that. So this can really reduce cost of one single evaluation. It will still not be efficient, but we need more, but that's one way to reduce simulation costs. Yeah, and if you do model reduction, I think I mentioned that you need to take care of the optimizers. Okay, let's look more from like the finite element stories from, let's say, the scientist point of view. Let's look from an industrial point of view. So I brought some pictures from an open source software that is actually used at least in small companies. It's free, it's attractive. So that just sums up everything once more, right? So you choose the physics in the beginning, so that defines your equation. Then you import a CAD file, lines, for example, or you have some kind of in-pool modeler where you draw some geometry. You choose the material boundary condition excitations, and then you have to assign them in the modeler. That are the working steps. Then this translates back to the underlying equation, defining the material distribution, excitation, and boundary conditions like in there, right? So essentially these are base distinctions. In which domain am I? Which kind of material property I have to use? And then you call the solver. The solver will create a mesh. That's a conventional workflow, not using like spline technology. And then you will simulate. Pool. In this case, it's a biconjugate gradient solver. And then you will get a field plot and quantities of interest. Now, there's the first time I will start with a bold claim, and I will think back to that, I think, on one of the last slides of this morning talk. I claim that kind of field plots are really useless. We show them, we like them, but they optimize. I mean, who's going to look at 10,000 field plots, right, and tell you, look there, right? Nobody is doing that. So what you want to do is you want to compare designs, and you do not want to compare them, let's say, on a level. That doesn't make much sense. What you want to do is you want to compare the designs in terms of these kind of post-processing quantities. That's I think a statement that you still need the PDE under the hood. Yeah, don't get me wrong. I think that we need the physics, right? But the creation of such images in context of optimization and uncertain manipulation is not relevant. So it will be different. So once you have isolated one specific design you want to build, and you want to compare your simulation data with your measurement data, and you will use data fusion techniques, also with machine learning possibly, then it might make sense. And you say, okay, I measured something there and my field plot is different. Then it might make sense to have field plots. But this is then not a parametric setting. It's a setting where I don't see machine learning useful. That's one design, one simulation, and there's nothing to learn in this particular case. So I want to say, yeah, if I get my point across, I will have a slide discussing that further, but that's like, I think, the first time that I think this may be interesting. And feel free, I mean, honestly, feel free to say something, say the opposite. I'm interested to hear your opinions. So then if you would do optimization, I mentioned already that shape freeform optimization is interesting. So you see that if you do very minor changes to geometry, I mean, this is magnified, obviously, but that will be the change, I think, 10, 20 times magnified. That these kind of changes significantly improve the spec of the machine. So as you can imagine, a machine should burn very smoothly. There should be no fogging, I think is the correct word for it in English. And so that you look at the Fourier harmonics of the movement, and if you see that higher harmonics pop up, that's bad, and you see that the design we proposed has a significant reduction of these kind of higher harmonic content, and this was an interesting object of optimization. Right, okay, so let's now do some step back. So I promised that I will try to keep the magnetic stuff mainly to this lecture to set the scope, but now let's do some steps back. So I like to distinguish between different kinds of parameters. I like to distinguish between parameters that are under our control. I will call them the deterministic parameters. Then there may be uncertainties, right? The angle of a magnet may change, so this I will call psi, and then there may be some range parameters that I also have to take care. And these are examples that I give you here. And there's a PDE to be solved, and obviously all these parameters come into place somewhere, right? So, and in the end, the solution, my vector potential A that will be constructed by finite difference, which might be millions degrees heavy, will depend on space. Yeah, well, of course, it will depend on this range parameter, because the range may be, for example, represented in the source or in the boundary conditions. It will inherit the uncertainties from the psi vector, and D are then maybe the optimization variables. Lines if you are lucky, or radii if you are. And then you have quantities of interest. I said before, in industrial workflows, these are up to 20 to 30. And they all can be derived, that's my assumption here, from that solution, depends on space parameters, and also the quantity of interest evaluation may depend on the parameters again. What this essentially does, it will either be a point evaluation, which is not numerically a nice measure, but what you typically hope is that this somehow involves some integral over the computational domain. Yes, so it will be, just assume that's a heat problem. So you will maybe point of interest will be the average heat on some plate or something, right? Then this will be, there will be an integral hidden in that whole function. Yes, please. I will come back to model uncertainty. So here right now, there are no model uncertainties. Yes, but yeah, no, that's definitely a thing. Although I mentioned before, in these cases we have quite high prediction quality, so it's not so relevant. So I think the business of model uncertainty, we have mainly treated in the context, not in the design context, but rather if you have measurement data and you want to get this, under one umbrella. So if you have a given device and you want to understand what's going on, and you have measurements and simulation, they don't match, and then you need to have this kind of fancy or ignorance or whatever people call it. Yes, but in this setting, and then like simulation design setting, well, you don't have measurement data, so you have to hope that your simulation is good enough. I mean, at one point you do maybe prototypes, but again, you will not do a million prototypes, but maybe a few, right? Because it's very costly, so it's not enough to deduce anything. Please. So the question was whether model reduction is, how this is linked to model uncertainty. Yes. Depends now which author you read. So, and I think I will have a slide later on, but we can also quickly discuss about that. So my understanding, I would keep model uncertainty and let's say simulation technology related uncertainty separate, because the one concerns rather the physics, right? I model the correct physics that I would call rather model, gray zone, yeah. So it's arguable, but what's the model for you and what not? But I would say model uncertainty is, so I neglected some. I mean, my question was hyperbolic in the beginning, so I neglected some derivatives. So this definitely gives me some error. So that's what I rather would like to call model uncertainty. And then there's like the defined element is introducing some error, right? The reduced base may introduce some error, etc., etc. This boils down to the point, and it's a pity that Giuliano is not here. So I know the model origin community, there are like two fractions, right? There are the people that say, well, it's a technique, and the others say the model. This myself well. So these are like two fundamental points of view on the same thing. So I could say, well, it's just a machinery that gives you less degrees of freedom. Then I would say it's a technique. And then you can say, well, now think about that, and now it's a new model. This, and then the question is it a model uncertainty or let's say a method uncertainty? Becomes grayish. Yes, sufficiently answered or agreeable? Yeah, but yes, but it's very different. I mean, so the model uncertainty I may not be able to fix. So with a POD or with a reduced Bayes approach, I just, there's a volume knob, and I just turn it, and I will give me more snapshots, and I know I will converge to a solution. And with physics, it's way more complicated because I have to model it, right? So I cannot just say, okay, give me more physics. In that sense, I think it's very important to keep those two courses somehow different, because I mean, yes, you may be able to quantify them, or to agree with you that you may not be able to distinguish between those two, but it's important to find out, right? Because if you have to improve simulations that do not match well, so what do? Do you need more physics or more snapshots? That needs to be decided. I think the answer is always, well, first try more snapshots, I guess, because it's way easier. And you have a clear understanding of convergence. Okay. And I will sometimes definitely misuse my notation here. So I will sometimes just talk about a function f of x, just because otherwise all the dependency will be crazy. All right. Let's do some first attempts to uncertainty quantification. So that's very important if you want to understand, for example, what kind of parameters do you actually need to optimize? Because we heard also this morning, you get templates with hundreds of parameters, but which one you actually want to vary, which one to vary. And then you can use obvious ideas, right? You can just do some classical sensitivity analysis. So you just do the derivative, which is also possibly difficult because you do not have access to the code. So you may do this fine difference in practice, but whatever. You compute a classical sensitivity. This is already not so clear, right? Because if you have uncertainties and if you have moving parts in optimization run, so if you look at this blue curve, then the derivative in the center is obviously 0. But let's say we have some uncertainties that vary between -1 and 1, then the derivative here is already much steeper, right? So the question is also, if you evaluate derivatives, where do you evaluate them? Because in uncertainty quantification setting, it's not so clear what is like your main point. The production process may be kind to you. It might look like a Gaussian, right? So this point may be very likely, but it might also be uniformly distributed. And this point is as likely as this point, right? And it has a different derivative, so a different slope. So classical sensitivity analysis is difficult. Then there are stochastic concepts, and I will back to them later in the third lecture, I believe. So you can look at the variance and don't look at this very complicated formula. This is like called a Sobol index. You may be aware. I mean, I'm sure some of you are aware. This is the idea is you take the variances of each parameter, let's say separately, and then you divide this by, let's say, the total variance you get from all parameters, and that gives you an idea which parameter was responsible for which variation. And this is also indicated in the picture by this blue. Right? The variance computes, let's say, differences from the mean. So this would somehow measure these kind of more precisely of the blue area, and would already give you a more, let's say, holistic point of view how to treat this problem. But eventually, you also see that you have to evaluate this integral, and this means quadrature, and this may be expensive, and this will be later on in the topic. Okay, so I thought, are there suggestions for an optimization problem for an electric machine? Anyone want to propose me optimization? What do I want to minimize? What do I want to maximize? Or any other product? Eventually, I don't care. So make a choice. It makes sense. And I'm looking for a suggestion of some engineering minimization. Please. Yes. 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 I would agree, but I would say that this will probably lead to an infinitely large machine, right? So you will. Yes, exactly. Yes, I agree. Yes. Yes, exactly. Yes. So, I mean, my point I want to make is that, and this was like, I think a good example, that you will have you need bounds. That was one thing, right? This should not be arbitrarily large. Very often, you also need to fix another component. So you typically have several entities of interest involved. So here I choose the opposite, actually. So, or maybe not. So we can say we maximize the torque. I like it. And then but we want to minimize, or we want that the energy consumption should be below some threshold, right? Because otherwise you will generate arbitrarily large machines. So my point here is, I think for any, well, I want to discuss with you that that's how optimization problems look like. And you rarely can optimize just for one goal. That's my point. And in this formulation, and that's the one I will be using in the slides as well, you see that the PDE is totally gone. It's essentially hidden in the evaluation of those differences. And I'd like to also discuss quick shortcomings of this formulation, right? So I mentioned that we have some uncertainties. So what is the meaning of this optimization problem? It's useless. I mean, if you want to really be very rude towards this poor optimization problem, you will, what's the point? You cannot manufacture this solution anyways, right? So there's no way you will get this machine that you have to optimize here. So, and then there are a lot of ideas that you can come up with, and I want to discuss with you essentially all these variants in the first lecture, I believe. So the idea is maybe you want to do a min-max problem, so you want, or a mix, you want to maximize something, but then minimum in some neighborhood, right? Because you want one of the worst machines out in the manufacturing space you have, or you want to optimize the average machine design. You want maybe to punish the variance, right? You do not want that machines have a big spread or devices or whatsoever, and or you want all at the same time, right? That's the thing, and this becomes, of course, like increasingly costly to do this. Okay. Now I would like to come to my bold statements. So I said in the beginning, let me do some observations. So spatially distributed parameterized fields are super high dimensional. So they depend on on space. So mathematically speaking, infinitely dimensional. Well, in the engineering world, these are millions of degrees of freedom, possibly, right? Then there is the uncertainty space, which is again maybe large, maybe again infinite dimensional. If a shape can take any form, can be formed arbitrarily, then this is again infinite dimensional, or it has to be discretized. And finally, I have my deterministic space. Again, if I have free-form optimization, it's infinitely dimensional. There is to a few length, radii, whatsoever, or maybe 30 of dimension of 30 r to the power of 30, which is still inconveniently big. And then we map all this to the R3. So and then the question is, I mean, you have to fulfill physical constraints, right? So in this case, it should, for example, it shall be divergence free, let's say. And then we are faced with the question that many machine learning techniques like pins, and if you do not know about pins, you will hear about it. So essentially the idea of pins, and I hope I don't spoil it, is that you put into the goal function if you are training, for example, a neural net. So you punish the net for not fulfilling the physics. That's the fundamental idea of those pins. But this just, is just one argument of the optimization of the goal function. So in the end, you don't know if your result actually for all potential points does really fulfill your physical constraints. That's inconvenient. And the question is, I mean, we know the trained element method has a very well understood convergence, which is even optimally. So that's why I personally, and again, it's a bold statement, and we can discuss about that, I don't see that learning fields makes much sense. I totally see that augmenting finite elements with machine learning techniques to model materials and these kind of things, that's like super useful. But there's a huge amount of literature on that storyline. I don't see it. And I will not talk about that, sorry. If you are here and you hope that I will do it. So my claim is that what you want to do, and again, right, you want to have fields or a field visualization maybe for a specific design. For one design, you want to have a look at it. Then a human is interested, then you need high quality. But if you do like optimization, you do really this on large meter spaces, I don't think you want to do this. And that's my claim. And luckily, you don't need this. And in multi-query scenarios, nobody's going to look at all those fields you may are able to compute. So that gives me, or that's like the guiding thought that we also had in our group that we came up with. So we are not touching the fields. I mean, so if you want to get field solutions faster, I think law reduction techniques make totally sense. Let's say learning techniques that require a lot of data to then extract those fields. I don't see it. Okay, so the fields are expensive to compute. I think another interesting observation that I want to share with you is, said we have like 30 quantities of interest in an industrial workflow, but we realized, and we saw it in different workflows, typically many of these interesting quantities are derived from one other processing quantity. Okay, that's a bit, I mean, okay. Let me first introduce the word intermediate measures. That's what some people that I know called it. So you have the PDE, you instruct some intermediate measures, some integral on some surfaces, these kind of quantities, and from those you can derive many other additional groups of interest. And that was a thing that we were looking into. So we propose, or I will discuss this with you. So we suggest to not learn all the different KPIs separately, but learn these kind of intermediate measures, and then still use, let's say, some kind of physics-based workflow to then extract the other KPIs from this guy, because that's a way to keep some of the physics in the loop. So we observed that if you learn an arbitrary KPI, it may have so many properties that you want to fulfill in the learning process and that you might violate, right? So I don't know, temperature may I mean, okay, now it depends, of course, how you're modeling it, but it may not be below 0 degrees, right? And on stuff like that. So this is very cumbersome to take care of that. But if you have some physical intermediate measures, then the derivation, I mean, it's physics-based, so it will make sure that stuff works, actually. Yeah, and that's clear. So and the leverage that we have is that our quantities of interest, I mean, that's what we need to expect, right? That they have some hidden smoothness, or that there's a latent space behind from which we can actually learn something. Another observation that is a bit counteracting what I said before. So what I know from what we do not do in my group, by the way, but what industry does nowadays, they store previous simulation runs. So they didn't do that in the past. So they just did one machine optimization or whatever device, and afterwards they throw away essentially the data. But I know from several companies now that they have created data, they start doing databases. So they really they do not keep the field data because that's way too expensive and large, but they keep, let's say, the parameter set and the quantity of interest evaluations. And that's still a lot of data, but that's manageable, right? And that is kept, and this allows you to have a lot of data available to learn from on a later stage. Again, field data is typically discarded because it's just large. Okay. I allowed myself to have a few memes, so that's the first time I'm experimenting with it. So that's one of them, and I realized it's a lot about me, which kind of memes I picked. But anyway. Are there any comments? Please feel free to comment. I mean, we're very interested to hear comments on my thoughts in the end about learning of quantities, how to include machine learning techniques into the design process. I mean, also on the online crowd, maybe there's a comment. If not, I will very slowly go to statistics. Please. So the question is, it would make sense, in my opinion, I mean, because it's difficult to answer that with gravitas to say, well, that's the case. That makes sense for specific areas. Still, right? I mean, if assume you do a multi-object optimization, you have 10,000, even if like on the size of a stamp, right? Still, it's a picture somebody has to look at. So I don't see that. So the only thing where these kind of data make sense if you realize something went wrong during your simulations, maybe, right? And it's very difficult from post-processing quantities to understand what went wrong. The simulation picture, you know, I mean, a trained engineer sees immediately, oh, okay, boundary condition was set wrongly. Okay, clear. I have to do it again. Shit, that happens. Do it again. And this is like impossible to see from a quantity of interest, I guess, or it's very difficult. These are the cases, but otherwise, it's only I see it only for debugging purposes. Even if you do the small one, I mean, it doesn't change the point that somebody has to look at. But I agree with you. I mean, also regarding this idea of debugging, yeah, maybe it makes sense. I mean, the data storage is for sure reduced, right? So that might make sense. So this problem then goes away. So already, if you have 3D simulation, if you can just narrow it down to some surface that's interesting to you or some cross section, I mean, storing pictures is already significantly more attractive than a 3D model regarding just the pure size of it, right? Because I will talk about that later on, but you're all aware, right? Because of dimensionality. So every dimension you get extra makes life a little bit difficult. Yeah, so yeah, it may be, but that really specifically depends also on, let's say, the optimization task at hand. So I can definitely imagine. So we had once we optimized a pole shoe of a accelerator magnet at CERN. So that's really, I mean, it's a rather big simulation model, but in the end, you only need like a very tiny piece of it. So I mean, we didn't store it, I think, but it would have probably made sense to do. I mean, just the area of interest. I mean, the good thing about pictures, and that's again only for 2D conventional pictures, is that they are very nicely accessible by neural nets, right? I mean, that's also a thing that if you have picture data, and I will also talk about that, that's of course interesting, right? And you can use the whole machinery from the front. I mean, then there's no physics. It's really like, image recognition, but this is, I mean, their machinery has proven to be very, very powerful. Any further comments? I was hoping that you would disagree more with my bold statement. Maybe they're not so bold. I don't know. I thought they were bold statements. I will try to rephrase for the next talk and evoke some protest, please. So the comment, and I agree that in companies, the people may want to look at selected designs on the Pareto front. That's true. But then the question is, what is now cheaper? I mean, do you store all the data, right? And do we then get those pictures easily? Or do you just compute in those three you maybe need to, right? That's, I think, but yeah, I agreed. I mean, that's what I meant before. So at some point in the development cycle, some engineer probably want that's agreed, but not, then the question is, it's not, I will claim how many fields can a human look at? Hundreds? I don't know, 100 models? I mean, that's like the limit, right? And then the question is, does model reduction pay, or machine learning, does it pay off, right? Because you may need the training data. And then the question, isn't it cheaper to just do 100 simulations than thousands, just hundreds? That's why I believe that for the fields, I'm not sure. Yes. The question is how we model uncertainty. Yes. So, maybe postpone the question a bit because I will definitely come back to that. Nonetheless, maybe I can give different kinds of uncertainties. Okay, there's even I have a slide on that. Unfortunately, it's not on that laptop, so I cannot just quickly open it. So but we can quickly collect kinds of uncertainties. Okay, so we discussed about well, there's measurement uncertainty. Okay, but there's no measurements, like physical measurements is not involved in my design process so far. There is uncertainty in the product manufacturing, right? You design something that will be then created, and there will be a difference because machines will not act perfectly, right? Then there are model uncertainties because I may have been sick and I forgot something very important in my model. That's probably the hardest to quantify. Then the numerics, right? I mean, I find element method may be regarded as something uncertain, which is actually, of course, not true, but maybe we don't know the error. So there's like also then some uncertainty regarding an element error. But I think the most interesting error for us now to think of is that these kind of manufacturing imperfections or material imperfections. So, and these can be modeled, I don't know, right? So I design, so I'm drawing on the board. I hope the online crowd can see. So let's suppose in my design, I have a template and there's a radius, and this radius is now, I don't know, it's 1 meter or whatsoever. In the manufacturing process will most probably change that radius, right? It will not be exactly 1 meter. It will be a less or a bit more, and it's even worse. This assumption is already not the truth. Why should the uncertainty in the radius be just in the radius? I mean, you would expect, depending on the process, that maybe this would be the uncertainty, yes? So that means if you model uncertainties, it's not clear that the design parameters you choose are also the ones that are actually uncertain. I mean, this would be manufacturing uncertainty. Yes, for example, yes. Yes. So, I mean, for example, you may want to simulate once the original model, then you want to to this, and maybe come up with a Fourier kind of idea. I don't know. So you may want to have a whole space of different models because they all can happen, and you want essentially to simulate all of them and see what is the worst case. Yes, yes, yes. That shall be the plan. Yes, yes. So, I mean, I agree. So I will talk about Caron-Löw expansion. So I'm not sure if that name was dropped already, but it's like essentially PCA that you heard already about, but I will now in the lecture. If I manage. So this will be one method which I would consider to be a machine learning technique to, I mean, have measurements to extract those kind of deformations. Yes, and I agree with you. This is like a different kind of modeling than I was mainly talking about. So I was mainly talking about to reduce the computational effort in the optimization loop. This assumes that you have already properly modeled this. And modeling this is, again, like a different task. And I will show you one method that is able to do this. And I will also show you one example how we did it, how this can be done. But this is, there actually, I know two cases how to do this. There is either expert knowledge, like the famous expert knowledge, or there's data. And both is difficult to get. I ideally you have a model that is parameterized in your deterministic parameter. So this would have been, I mean, I call it R because it's a radius, but then the nomenclature of my slide, that would be D. And then I would have maybe, I think I call that psi, right? Psi would account for certainty. And yes, this needs to be modeled to some extent by a human. And I don't think I mean, there are machine learning techniques like Caron-Löw expansions that can help you to do this, but I'm not aware of a fully automated system or anything that does this. And if anybody is aware, please tell me. So, but mainly in navigation, you need some experts. And I would say 99% of the cases, people just would now change, would say, okay, that radius was supposed to be one. Now let's say it's not one, but I do add, and we'll talk about that more. I will just add some normal distribution to it with some randomness, and that's my uncertainty. And that's really, I mean, I don't think I have a slide on that, but this is wrong, right? This is there's no point. Why should, if you don't know your production process very well, why should the radius be uncertain, right? It can be, yes, but it can be anything, right? So there's confusion, and I think especially now I blame the mathematicians and the mathematics community that developed these uncertainty quantification techniques. In a lot of cases, they just both parameters made them random because it's easy. But from engineering perspective, I think this is too short. So this is in a company or for your research, modeling these uncertainties is a crucial part, and is time consuming. Okay, so I think the slides tell me I should continue. Because I have, anyway, it's a statistics part, so I think I can be quick here. I hope. Did I roughly cover it, or I don't know? Yeah, I hope so. But I don't know Caron-Löw expansion. I'll come to it, and I think that's quite easy and beautiful. Okay. And actually, Giuliano probably did all the work already with SVD for me, so I think I can do it very, very short. All right. So since I really have only 20 minutes for those slides left, and I don't want to be. Somebody took. I don't know. Honestly, okay. Online crowd, there's a fly on my screen. No, that's not happening. Right. Thank you very much for pointing this out. Right. Okay. I'd like to be quick. This concerns probability theory, and I'd like to distinguish between probability theory and statistics. because statistics is like the simpler case where we just deal with given data, right? And obviously more the mathematical framework, and I will discuss the difference much in the upcoming slides. I like just to convey some information, because in the end, as I mentioned, we have to model things with stochastics, and as I mentioned, it may be that some of you just had, never had any course on stochastics. I thought I should put some basic notion on the slide. So the first, the easiest thing is the sample space. That is actually, well, the space of the elementary outcomes. And then an event is a subset of this. So, for example, a combination of these outcomes. And this sounds very theoretical, but if you look at it more practically with an example, it immediately makes totally sense, right? So if you roll a die, then the outcome space 1 to 6, and then you can have events like the result is 2, or an even number. So and already even number is the combination of essentially 2, 4, and 6. So it's already a bigger set of things that can happen. This can be general, or it can be with more complex examples, right? You can toss a coin and distinguish between heads and tails, and then, for example, you may ask, okay, what's the probability later on that the first toss is heads, and then you get essentially 4 cases. And if you are familiar, or if you just have a good intuition of probability, you immediately realize, okay, so what I need to do is to understand how often this occurs. I have to take the quotient of those two, right? That's very natural. And you will see that this should be 8 outcomes. So, and here we have like four good cases. So 4/8 is 1/2, and that makes totally sense, because all this would not have been necessary, right? Because tossing a single coin, we know it's 1/2 for each side. So it's like a very complicated way to look at this, but just to give you a feeling how this works. So indeed, that's what I did was, I assigned a probability to such an event written like with, and this shall be between 0 and 1. And this can be perceived in the notion of the class by, well, we have the number of favorable cases of the good cases, and we just divide by all the others, and this gives us this probability. This is mathematically not super precise, but I will put it under the rug and not discuss this in much more detail. I think that's totally sufficient for us here and today. And if there are mathematicians in the crowd, they probably know better, and yeah, and anyway, and know it better. So yes, so this can be general. Can be used for multiple events, right? So in this case, if I throw a coin n times, again, I can have head or tails. And then the sample space is 0 and 1, and this spans a product, so again and again n times, that I get a vector as an output, and then, for example, the number of tails, if I assign it to 1, will be then just the sum of it. So that's the idea, to assign a random variable to it, right? So before I called it heads and tails, and now I call it 1 and 0, and that's the idea, to make this more matchable by mathematics, right? I want to have a mapping that I can actually do with it. So especially for uncertainties, I will most probably have continuous random variables, right? So I barely, in certain situation, one more coil than I originally foreseen. I think this can happen. I remember once in my life, I bought rolls at a bakery. I got 1 roll for free, right? That's like the case. It can happen, right? It's a discrete random event, a discrete uncertainty, but it is once in your life that you get a roll. This is not the case. We are looking at like spatially distributed real number kind of situations. So then these probabilities are assigned to events. And in the discrete case, typically have this case, right? We have the random variable is either 1, 2, or 3, so it equals a constant. But for continuous random variables, this notion does not make sense. So there you have like notions like this. So x shall be smaller or equal than c, x shall be bigger than c, or x shall be between a and b. And that essentially means that you have all the events between those 2 bounds. And this gives then immediately rise to the distribution function that you are probably, if you have ever dealt with statistics, that's probably the thing that you will definitely remember. So you have essentially this function that gives you, according to this definition, right, for every it gives you back the probability. And this is called cumulative distribution. Then you have, let's say, the iterative way of expressing that, which is the probability density function, and they are essentially linked towards each other by the derivative. So that means the PDF, so the f is essentially the derivative of the capital F. It's typically in the textbooks, it's introduced as an integral, because if I write it as a derivative, I need to make smoothness an assumption, right, to be allowed to take the derivative. But if it's the integral way, it's more general, and that's why it's typically done like this. But essentially, they are linked by taking the integral or taking the derivative. Okay, let me come and quickly discuss 3 cases, and then I will also link that back to uncertainty quantification. So there is the uniform distribution, which is like most well known, right? So we have some interval, we define it between A and B, so that's written by a calligraphic U. So my variable shall be between those 2 bounds. So for example, it shall be between 0 and 1, and then they have all the same probability, right? All the values have the same probability. And I want to make sure that this area needs to be an integral area of 1. But implicitly then also defines the probability. Or I can have it between 0 and 2, and the probability is 0.5. This is the probability density function, and then we have the corresponding integral that looks like this. Okay. Very basic stuff. As I said before, I really want to just do it such that you grasp some notions if you have not been aware of it before. Then we have the normal distribution, probably even more well known, the L curve here on the right, which is specifically interesting for modeling these kind of random variations in processes, right? Because you would expect that if a company creates a design workflow that they will be, but that the expected or the design that they want to produce shall be the majority, right? So that's what you expect. And that the larger the deviation, the more rare it gets, right? That feels like a very natural function or distribution for modeling uncertainties. And then there is a log normal distribution. You find that also in many papers regarding uncertainty quantification, which depending on the choice of parameters, I mean, it's essentially, right, it's connected to the normal distribution, but there's in between like the one exponential function, and this has the specific beautiful effect. I mean, you see some pictures of it, that you can ensure that there are no negative samples drawn from the distribution, right? So it's only strictly positive, because it's a normal distribution, but then it enters the exponential here, so there's no way to sample something negative. Now let me connect that back a bit to how to model things, right? So there are 3 distributions, just the 3 most common ones, and there are many more, and how to do that now, right? So what you should do, and you should the distribution, right? You have data, you have inspected your manufacturing process, you have looked at this curve, you have taken specimens, and then you measure it, and then from that, we'll show you how to do that with Karl-Löw expansion later. You deduce somehow your uncertainties or your distribution. That's rarely the case. So I think I have 1 or 2 cases where we actually managed to get this because of plenty of reasons. So even within the companies, they don't know this very often, right? And if they have it, they don't give it to you. And even within the company, you know, the people that are in charge of measurements may not talk to the simulation guys very often, and they don't want to give their data even within the company. So it's really, really difficult. So that's why what most people I think should do, and maybe also do, is just model everything with uniform distributions. And there's a nice principle of indifference. I really enjoy the title of that statement. I think it goes back to Nulli, I think. So it essentially says, if you don't know anything, well, then everything is like against each other. So that's like a statement that if you ask engineer what are the uncertainties, and he or she tells you, okay, it's, I don't know, 1%, and then, well, you could think about doing it with a normal distribution, right? You could say that the red, this, well, isn't by the standard variance, so you could say, okay, I take that to be as what the person told me. But I think what you should do, and I'm following here that's this rule, that the uniform distribution is then most probably the most honest choice to do if you don't know much. Although I think the normal distribution is very intuitive, there's one additional drawback that you have if you model uncertainties with normal distributions. It has infinite support. So even if you shift and I go back to my picture of the normal distribution, even if you shift by changing the mean value to a very, very large value, right? The function has infinite support. So there's a non-zero probability that you have a very, very highly negative value. That's just unavoidable. And this is, of course, I mean, in an abstract mathematical context, that was probably ingenious by Gauss to come up with this. But in practice, that's very annoying because you definitely do not want to have a negative radius. So that's not what you expect that the company will produce. So that's why the standard, the conventional normal distribution is not always a good choice. And if you choose, I mean, there are ways to play with that. And one thing are truncated Gaussian distribution. Okay, and then and I think that's also the main reason why log normal distributions have been very popular in many papers from the math community. You find it because it generates always positive values, and that's of course interesting because then you cannot get these strange situations with negative radii or whatsoever. But on the other hand, the question is if these log normal distributions are a realistic model of anything, right? I mean, there may be cases where the log normal distribution is exactly the right choice. I never have seen one yet. So, nothing ever looked like or was like a perfect fit for. All right. I like to talk quickly about moments. So that's also very intuitive stuff. The most basic idea is like you take the mean, right? And the mean somehow can be understood as the center of mass. So you have different probabilities. These probabilities with a value. The product is then just summed up, or if we'll see in a second, in the continuous case, we'll integrate it, and that gives you your expected value. Here's the notation for the continuous case. We have the outcomes. They are depend on the stochasticity. Then we have the corresponding measure. I think for non-mathematicians, not very accessible. So I think this is way more intuitive. So let's immediately look at those definitions where we can make use of the probability density function in there, right? So that feels natural, right? This is the probability multiplied by the value of the outcome, and then we integrate over R. Or if we have distribution that has a support, a local support like the uniform one, then we only have, of course, to integrate from A to B and not over the full domain. Important thing about the expected value, it's linear. So if you have two random variables, A times X plus Y, then it's A times the expected value of X plus the expected value of. And we can define like arbitrarily high moments. So essentially by taking the expected value of the kth power of your random variable, it can be done for the so-called raw moments. And it can be done for the so-called central moments. So they differ only that you see you subtract within the brackets, subtract the expected value, and this makes sense, right? You look at, imagine the normal distribution, and now you just shift your data to the center, right? That's why it's called the central moment. You reshift it. That gives you then a more, let's say, balanced, more, I don't know, more natural way to quantify those things. But that in some sense, they are both with each other, but this one is, I think, particularly interesting because the variance is a special case for k equals 2. So k equals 2, so m tilde k equals 2 is exactly the definition of the variance as given here, which measures, as the word essentially says, and as you know, the variation, right? So the width of your Gaussian bell curve, for example. The variance is somewhat quadratic. That also makes sense, right? The k was 2. So that means if you have a random variable and you take a times x, then if you move the a out of the integral, square it. And if you shift the variance, so if you have a random variable x plus a, then this is somehow compensated because you anyway subtract the mean. So this a doesn't play a role, so you can just drop it. For engineers specifically, I think the standard deviation is the more natural way to look at things. So it's essentially, well, it's roughly the same, but you take the square root. But the beautiful thing of taking the square root is that this again has the same units as your expected value, right? So if you look at the quantity, which is measured in meters, and the standard deviation is again in meters, while the variance is in meters squared, which is inconvenient, let's say, from a perceptual point of view. But regarding measurements, so if you want to optimize, so you don't care if you minimize the variance or the standard deviation, right? And most probably you would rather optimize the variance because you get rid of the square root, which is probably ugly in your optimization scheme. So it doesn't matter because it's just a scaling issue at that point. Yeah, and by the way, that's a word of warning, so that I in many textbooks on stochastics, it's not explained. And if you do this stuff numerically, I mean, this is mathematically exactly the same. So it's just easy to use it, those are true. But if you use that formula, which looks actually nicer than this one, it's numerically a disaster. So if I did it once, I did some computations, the result was odd. And afterwards, I realized that in some textbooks, they tell you don't use it, but not all of them. So that's why I thought, since you are probably numerics fine people here, so I just want to make sure that if you have to evaluate the variance, please take the left formula, not the right one. Okay, so we talked about the Gaussian distribution. So this is a specific or a very interesting function. It has the advantage or the specific feature that each function is completely determined by its expected value and its standard deviation or variance, as you like. So with two moments, this function is totally fixed. And I only mentioned that the distribution is not maybe great for engineering modeling and that you have a truncated distribution. Yes, please. Yes. 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 Yes.
Then you get the standard deviation in the vast majority of cases. Then standard deviation is so small.
Yes.
Probability of sampling negative values is you will never sample it with the long time than the
Yes.
failing of the company.
So the question is, or the comment which I very much agree with, is that if you manufacture something and you make statistics, that you will never ever get a negative value, of course, and even not very large deviations will not occur if you have a good process. I agree. But if you do Monte Carlo sampling, I have not yet explained Monte Carlo sampling, but if you draw random numbers, you have no guarantee because a random number generator might draw for you a very negative number. So if you replicate that experiment on the computer and you model it by a Gaussian curve, you may, by luck or by the opposite, you may just draw minus 10,000 for that radius. It's possible, right? And then you have formulated physics. Okay, so I mean, I don't want to make that a bigger. I mean, I agree it rarely happens, but it's a case you have to make sure. So that there are two things about that. So first of all, the easy cases, you draw random samples, and you just throw away the ones you don't want to have, and probably nothing changes, right? But that's an if statement you have to make in your code, because otherwise you are unlucky, you hit it, and it crashes, and it's a simulation of days, and you are very unhappy afterwards. Okay, easy solution. There's one patch if you do it like this. So very mathematically speaking, well, the integral should be still exactly 1, right? That should be. And if you just throw away samples, you violate this. And that's why people have come up with this truncated normal distribution, which essentially just they make sure it goes 3 to 0, and then they rescale it a bit to really have 1. And if you have a random generator that can draw from that distribution, I would say it's a bit cleaner. In the end, it doesn't, I agree, it doesn't make much of a difference. But it's an annoyance, and that it's very often not properly discussed, and that's an issue that I mean you will run into for sure. Either you know it and then you make it easier, it's statement in your code, yeah, or you get it in the painful way. But I agree, these are super rare cases. But again, if you do 10,000 Monte Carlo samples, I mean, you may be unhappy. Okay, agreed? Yes. So another question or comment maybe. Yes.
Derive empirical results for your integral relation. So does it?
Yes. Yes.
What you have.
So the question is, if I do like, or no, on the numerics level, if I use a truncated Gaussian distribution, but I do the math, let's say on the formal level with the real Gaussian distribution, is that potentially dangerous? We did that, for sure. We didn't observe anything bad happen. I agree, but that's like how you do science, right? You simplify the model at some point, you prove something that you can prove, and in practice you do some tricks, get it done. So I'm afraid I don't have a proper. Maybe you can do even estimates, but I don't think it's necessary to. I mean, these are only very rare cases we are talking about. So, yeah, but that's how we did it. So we actually did some. I'm not sure if I talked about this. It's some gradient-based method. So where we needed gradients. And we compute the gradients for the normal distribution because for it you have closed form solutions. But for the truncated Gaussian, you don't have closed form solutions. And we let the gradient optimizer use the wrong derivatives, and it worked like super nicely. So, yeah, we exactly did that. Yes, yes. You also had a similar impression, or yes, yeah, that's also true. I mean, of course you don't know if your model is like super sensitive in that area, but yeah, you should hopefully know. And especially, I mean, if that's indeed the negative part and at the radius, it should actually be in the tip there. Okay, so I'm running out of time. Let me check where I can. Okay, let's do the following. So I suggest we stop here. I will talk a bit about random vectors, and because I really would like to discuss, especially because there was interest in the audience, I would like to. I mean, if I speed now through this, I will definitely not explain Caron-Löw very well. So that's why I would suggest I stop here. I do this after lunch, if I recall correctly. Yes, then I'll do my 2 blocks, and I think I will just manage with the rest. Thank you very much for the attention. I suggest if there's a question left, please come to the front. Then the others can already go for lunch. Okay. Thank you. And also for the online audience, maybe you can just write it in Teams for me or send me an email. Thank you.